Thank you very much. I felt a bit uncomfortable with this pop. And so I opted for the simpler option. I hope you can hear me upstairs. It's a great pleasure to participate in this meeting in honor of Professor Srinivasan. Although I have not worked with him, and I hope I will work with him. And it's also, I would like to thank Shravan and Rama for inviting me to this meeting. I think Shravan had visited us at Ayuka to give a colloquium, and suddenly while we were chatting, his eyes lit up saying that, maybe this is a bakra for light years. I mean, bakra, I hope you understand. So that's how I got into this. I should start with a story. I mean, basically, when I was a kid, these exams where you write essays are a complete nightmare. And so you kind of try to prepare for something. And my mother, I think, told me that, this Tamil essay, what is going to come is you have to write all about cows. And I prepared everything about cows. And then suddenly you go to the exam, and there the topic is horse. So if some of you understand Tamil, I was under time pressure to finish this essay, and I said, Kudaraikku rendu kombu undu. This is the only line I wrote. Translated means horse has two horns. So basically, the thing which I work on is magnetic fields, and turbulence is not something which I think about separately. But then when I was asked to talk in this meeting, I started thinking, I am supposed to talk about turbulence on cosmological scales. In fact, if you see in the program, I've been given a special color, it looks, cosmological turbulence. So then I realized that wherever turbulence is there is magnetic fields, at least in the astrophysical context. And so these two things go together, and so I could kind of relax, and it was not going to be completely disaster. Let me begin by saying that I have enjoyed working with a large number of collaborators. The first 3 lines of students, the last 2 lines are faculty. Pallavi is my last student. She is now a postdoc at MIT. Luke is at Rochester. Sharanya is here in Bangalore at IA. Pranjal is already a faculty, and these are PhD students. So this is the kind of summary that I'm going to add turbulence wherever there is magnetic fields in my previous slide. So the universe is turbulent and magnetized, okay? And I'm going to discuss 2 different themes. I'll spend less time on the turbulent dynamos because that's something which may be more familiar to some people. I'll spend a bit more time on early universe, hopefully, because that's something which you may not have ever heard about, some of you. I'm sure some of you have. And I will say many things which are going on in the kind of things that I think about have a lot of inputs from the kind of things that many people do in turbulence. And so I'll talk about turbulent evolution and some signals for this early universe kind of stuff. So if you're interested, there are 2 reviews. There's a report on progress in physics, which I really love to make this title, The Origin, Evolution, and Signatures of Primordial Magnetic Fields. And if you're interested in the dynamo stuff, there's a review long back with Axel Brandenburg. I cannot right into it. So the universe is turbulent and magnetized. If you look at galaxies, Professor Srinivasan showed this very nice picture of a supernova remnant yesterday. And these are the main drivers of turbulence. The turbulent interstellar medium is due to randomly exploding supernovae. And they, among other things, among mixing metals, which is what he was talking about, also generate the magnetic fields that we see in these systems. For example, this is an image, an optical and a radio image of one of the nearby spiral galaxies, M51. And you can see what is shown here is the light stuff is all the stellar kind of light in a nice spiral arm. It has a companion. And the contours indicate radio contours of radio emission, synchrotron emission. So this whole galaxy, which is about 10 kiloparsec scales, okay, 10,000, I mean, a parsec is about 3 light years, a kiloparsec is about 3,000 light years, and 10 is 30,000, is filled with magnetic fields and relativistic electrons, and of course, turbulence. And you can also see lots of large-scale ordering in this. And one of the things that we are interested in is to explain these large-scale ordered fields that you see in some way here in this polarization kind of map. If you imagine supernova stirring the medium, each supernova remnant expands maybe up to tens of parsecs, and they are hitting the interstellar medium randomly at random times. So the scale of the stirring is about tens of parsecs. The scale of the galaxy is about 10 kiloparsec. And there is here something where stuff which is not so much ordered stirring leads to a very ordered kind of object. And that's a thing of great interest.
What is the stirring, the large-scale stirring? What is the process of stirring?
Is the supernova explosions, which are hitting the interstellar medium all the time. Yeah. Now, if you go to bigger objects like galaxy clusters, they're also turbulent. And they're turbulent due to a different process, just the process of structure formation. So here I've taken a cosmological simulation by Dongsu Ryu and company. What is shown is density, shocks, location of shocks, and vorticity in a color-coded way. Basically, you have gravity driving gravitational instability to form structures of bigger and bigger scales in a hierarchically clustering universe. When some structure forms, it's not going to form in like a spherical manner. It is going to have some oblique, it's going to produce oblique shocks. It will generate vorticity. And this vortical motions, for example, it's color-coded vorticity times the age of the structure is about 0.5 at the lowest level and 100 in the highest regions. So there are several eddy turnover times for it to cascade to make a turbulent kind of medium, even in the cluster medium. Yes, it's 25 megaparsec here, and that little dot is like a galaxy cluster which is forming there. It's about a megaparsec. And more or less similar process will occur even in a forming galaxy, even before the first supernovae go on. And more or less similar process will occur even in the forming star as it's trying to form, and there will be things which will stir up the medium. So if you can go in two different ways. If you go to higher and higher redshift, younger and younger universe, and ask whether those galaxies are magnetized and turbulent, it turns out that they are magnetized. And there is some tentative evidence which I will not talk too much about, but we can discuss later. What's been very interesting is in the past half a decade or so, there is some tentative evidence that the intergalactic medium, even in the void regions, devoid of galaxies, could host a weak magnetic field. And there's a kind of a lower limit on the magnetic field that they could host. Let me just rapidly tell you what the evidence is. The evidence is you have a blazar, which is a very active galaxy, which is emitting very high energy TeV gamma rays. These TeV gamma rays are propagating into the general intergalactic medium. They interact with the background EV photons. And so they produce electron-positron pairs. These electron-positron pairs are still highly relativistic for 10 TeV and all that. And then they interact with what is called the cosmic microwave background, which is pervading everywhere, and produce GeV emission. So associated with every TeV blazar, you should see a GeV emitting halo around it due to this secondary cascade process. And what people found is that these are the kind of sensitivity, this is the predicted GeV signal, and this is the TeV observations of the blazar. And this is the predicted sensitivity of the GeV telescope, but you don't see this emission. And so people ask why.
Does it influence the CMB?
Backward. The CMB influences it, but the energy in the CMB is too large to influence the CMB, absolutely. So what people argued that suppose there is a magnetic field in the intergalactic space between galaxies, that could deflect the electrons and positrons in different directions, and that would spread out the GeV emission. If it spreads it out enough, then you will not see it in these observations. So what kind of field do you require? you require about 10 to the minus 15 Gauss or so. Now, the mean free path for this TeV photon to produce pairs is about 50 megaparsec or so. By the time the blazar is here and the TeV radiation goes out, it's already in the void type regions. And that's where you should get the magnetic field. So this is a very interesting development from gamma ray astronomy, which seems to indicate the presence of some weak magnetic fields in the intergalactic medium voids. But of course, it's a very indirect evidence. And it reminds me of another story which my supervisor, Jain Narlikar, told me, that he said that wall there is a picture of a cow eating grass. This wall here, if you want. Then you ask, where is the grass? The cow has eaten it. And where is the cow? It went away after eating the grass. So from almost no observations, you can make a complete theory of what all happened there. And more or less, that's what's being done here. But okay, it's pretty serious stuff, and one should have more direct evidence for this. This? Yeah, this is the point spread sensitivity of the gamma ray telescope. Upper line is the predicted GeV secondary emission. Absolutely. So, they are detected here. They are these guys. That's how allows you to calculate the GeV emission. Absolutely. So what does it mean? You can put various limits. I will come back to this later. So what does this all mean? So you have turbulence everywhere, you have magnetic fields everywhere. How do you explain this? And I'm very happy to note that I'm talking later than Arnav, so he has already given you a fantastically nice introduction to both MHD and dynamos. So one possibility is that the motions due to turbulence induce electric fields, and they change the magnetic field, and magnetic fields are maintained or generated by electromagnetic induction. Now, where does turbulence come in? Turbulence is a very useful thing to exponentially grow magnetic fields. Basically because if you take two parcels in the fluid and they're connected by, let's say, some flux tube or something, turbulence allows them to walk away randomly from each other on the mean square sense. They will elongate the flux tube. That means if you have almost divergence-less motion, they will squeeze it in the perpendicular direction. Simple flux freezing means the field will grow. So it's very easy in the presence of turbulence and a weak seed magnetic field to grow the magnetic field rapidly. What is not easy is to make it coherent enough. And so making it coherent will require a lot more effort, for example, and a lot more thought. So it's very easy to make a magnetic field, but you cannot address this question qualitatively by waving hands, because the rate at which you grow the field by random stretching turns out to be comparable to the rate at which you dissipate the field because you've squeezed it into narrow regions where the currents can dissipate. They both will balance each other. Which one will win depends upon either doing a detailed numerical simulation like some of the things which Mahendra has done or we have done, or more interestingly, yesterday, Kriknen was mentioned. This person, Kazantsev, did exactly the same thing for the MHD problem. He assumed that you have a velocity field which is delta correlated in time. When it's delta correlated in time, this induction equation with a stochastic velocity field can be transformed into equations for the moments. Within 4 pages, he derived the equation for the second moment, transformed it into real space, translated the problem of growth of magnetic field into a bound state problem in a potential like this, and said bound states, if you have bound states in this potential, fields can grow. And it turns out that provided you have magnetic Reynolds number larger than about 100 or so, you get these bound states. So under fairly weak conditions, magnetic fields can grow. And it turns out that if you put helicity into the same problem, if you make the velocity field also helical, then these bound states, this potential problem also opens up the possibility of tunneling. So there's a very elegant way of looking at dynamos. The fluctuation dynamo or the random field dynamo is equivalent to a bound state problem. The large scale field generation can be mapped to a problem of tunneling in this kind of potential. So this is something interesting, but there are two problems here. One is with the presence of this rapidly growing fluctuations, can the large-scale field grow? And there's also a very interesting problem, which I will not go into in great detail, but which has occupied many of us for a long time, is magnetic helicity is a conserved quantity. When you make large-scale fields, toroidal and poloidal fields are linked together, you have created helicity. And there must be compensating helicity on small scales, and they will back react, and the Lorentz force due to that will kill the dynamo unless you do something to transport out such helicity. So let me just move on and say we have tried to look at this problem. For example, the fluctuation dynamo problem. Can the mean field dynamo operate in the presence of fluctuations through direct simulations? And even though you get large power in small scales early on, at later times you can transfer that power because of Lorentz force to larger scales. I won't say too much about this. These are simulations by Pallavi, basically. And you can, if you assume the mean field kind of treatment, you can also explain things like that galactic spiral that you saw. In this particular case, the outflows from the spiral arms are enhanced along the spiral arms, and they lead to nice spiral patterns. And as I said, you can form dynamos even in forming stars. Let me move on to the other thing, which is quite interesting. Can you make magnetic fields in the early universe? Now, why should you want to make magnetic fields in the early universe? Because, for example, it could provide a natural explanation for magnetic fields in stars. In the void regions, which are devoid of all these structures which are turbulent. So can it, for example, it can provide the seed field for a dynamo. It can also help induce coherence. So what do you do in the early universe? One number to remember is that if you take what is called the cosmic microwave background radiation, that is the radiation which fills the universe, and you ask the energy density in that, if it's completely transformed into magnetic fields, what magnetic fields do you have? It's about 3 microgauss. So if you can put even a millionth of, or a 1/10 of a millionth of the energy density in the universe in some way into long wavelength magnetic fluctuations in somehow, then you could make coherent fields, which are interesting because fields of order of about 10 to the minus 9 Gauss on galactic scales are interesting for galaxy formation, cluster magnetic field, etc. Okay? And it'll be interesting to probe some physics of the early universe if you actually detect such fields. One thing which I should also emphasize is that the way we measure these fields is that we say that the universe is expanding, all areas expand. So if your flux is frozen, the magnetic field into expansion factor squared is a kind of constant. So you refer everything to today's redshift, and that's where I put this nanogauss to today's redshift. So there are various processes going on in the early universe. For example, there are various phase transitions like Electroweak, quark hadron, and inflationary phase transition. In principle, any one of these could be sites for magnetic field generation. And when I say magnetic field, I also mean turbulence, because once you have generated the field, that will drive motions. Okay? So people have looked at this. For example, if one of these Electroweak or QCD phase transition is a first order transition where you create bubbles and the bubbles collide, then this will automatically lead to stuff being stirred up and stuff being generated, seed fields being generated, velocities being generated. But there is no real thought about, at present people do not believe the QCD phase transition is first order. They think it's what is called a crossover. And the Electroweak phase transition also is not believed to be first order. So this is not at present in a great thing. The other thing is that the region of causal contact is about 10 to the 15 centimeters expanded out to today, and about 1 light year, which is very nice. That's the light year in Shravan and Rama's poster, if it's the QCD epoch. These are very small scales compared to the kind of scales that you're observing the magnetic field in. So another possibility is inflation. Now, inflation is a very interesting idea that the universe underwent a very exponentially rapid expansion very early on. And this is invoked to solve various problems which come in the standard Big Bang cosmology. For example, the cosmic microwave background is kind of uniform wherever you look, but these different bits of the sky were not in causal contact at the time. If you started in a purely Big Bang universe, and inflation allows the whole observable universe to be made into causal contact at some early point in time. The other interesting thing about inflation is you can start from small fluctuations, and which are quantum fluctuations at some small scale, and then expand it to generate classical density fluctuations at large scale. And this is exactly how we think all the structures in the universe arose. So one possibility is, can you make primordial fields like that? So the vacuum fluctuations in some corresponding field of the electromagnetic wave is used to expand out and generate magnetic fields later on. So the other thing going for it is that there's negligible charge density. When you expand very rapidly, you dilute away all the charge. So you free yourself of the stranglehold of flux freezing. So if you have an electromagnetic wave fluctuations as a quantum fluctuation, then you expand it out and make it into a classical electromagnetic wave. Of course, at that epoch, it's not electromagnetism, it's something else. And then the universe transits at some stage from this inflationary stage and reheats back to produce all the particles that we love. Those charged particles will short the electric field. It's like capacitor. You have an electric field and you suddenly put charged particles there. You discharge the capacitor. And they'll freeze the magnetic field. So what started off as an electromagnetic wave in vacuum will transit to a magnetic field in the universe after reheating. So this is the basic idea about inflationary generation. I won't go into the mechanisms that we have looked at, but only say that the present models are all not great. For example, some of the models that we have considered seem to require low scale of inflation and also pretty blue spectrum of the generated magnetic field. I will not talk about this much. Once you have this generated magnetic field, two questions arise. How does it evolve, and how do you detect it? So let me just say a few things about both these things. Now, you want to now do MHD in an expanding universe. What helps you is the fact that the magnetohydrodynamics that we all are used to can be just taken over to the expanding universe, because there is a conformal invariance of resistive viscous MHD. So basically, because you can write down the expansion in an expanding universe, you take all the relativistic Maxwell equations, the fluid equations, the Ohm's law, everything you can write down, and you can transform to these variables, which is natural. For example, flux freezing would have told you BA squared is constant if there's no peculiar velocity. Similarly, electric field, charge density, current density, matter density, pressure, velocity is left invariant, because in terms of these conformal coordinates, it's the same. dx by d tau is same as dr by dt. And all these equations can be taken over to flat space equation. So whatever intuition that you learn in flat space MHD, it can directly be translated into looking at what happens in the expanding universe. For example, all the magnetic stresses will produce metric perturbations, including gravitational waves, which are important to mention in the present climate. Lorentz forces will produce almost incompressible motion because magnetic pressure is pretty small. And the conductivity, if you calculate, it's pretty high. Viscosity is important whenever particles are decoupling, whenever neutrinos decouple from the universe, whenever photons decouple from the universe, viscosity is important. The Prandtl number, magnetic Prandtl number, is generally much greater than unity in all these epochs. And so basically you have an interesting dynamics to set up, okay? And for example, if you take an Alfvén wave, these turn out to be overdamped because in the viscous regimes. So you can follow through all the evolution. Now, in many of these things in the phase transition, you get these blue spectra. So that set up decaying MHD turbulence because given some magnetic field and you have an Alfvén velocity and the wave number and the universe's age tau, when this condition is satisfied, the Alfvén wave can oscillate once. And once the Alfvén wave can oscillate once, or more as the time increases, it can kind of induce motions in the fluid. So now this turbulence is very different. It's a turbulence driven by the magnetic field in the fluid plasma. It can drive motions in the fluid. That motion can decay, and you will get all the kind of stuff that you are used to. For example, this is how people believe the hydro turbulence would decay. These are some things which figures I've taken from Axel Brandenburg's paper in 2015. You preserve these large scales and you just keep cutting. Okay? And there was a talk the other day, and these are the scaling laws. For example, if you put n equal to 0 here, you'll get your b squared going as minus 1.2, and correlation scale going as tau to the 4/5. This tau is now the conformal time. It's a time which has transformed out the expansion factor of the universe. So you can use all your things which you love and then transform back to the real things. On the other hand, when Axel, for example, did this simulation for non-helical MHD turbulence, he actually did not find in higher resolution that it did this. It just kept cutting the tail here, but the peak also kept shifting, even in non-helical MHD turbulence. Something not yet understood completely, and something which was debated quite a bit after he published this result. And so these allow you to follow the field after generation. The K0 is the forcing, initial forcing, I think. Yeah, but this is magnetically forced. So you are putting magnetic field somewhere here, okay, and then letting it decay. It induces, sorry, I should explain more. These dashed lines are the velocity spectra, solid lines are the magnetic spectra. They induce velocity field which are subdominant, but that's of course driving the evolution. The evolution can only be driven by the V cross B term. So that's cascading the magnetic energy. It decays. Here it would have decayed as B decayed for n equal to 0 is 3/5 is actually finding, n equal to 2. Magnetic field would have decayed as, what is that? 5/7, and here it is 1/2. So actually this decay is slower. And if you have helicity, for example, the decay is even slower because of magnetic helicity conservation. Here the peak also shifts to larger and larger scales, and you have, because of helicity conservation. I have only 2 minutes. So these will all predict some strengths and some coherent scales for you. Now, in the last 2 minutes, okay, these models can explain. Let me just say, how do you detect such fields, for example, in the cosmic microwave background? Basically, because of the presence of these inhomogeneous magnetic fields, you have metric and velocity perturbation. Because, for example, the magnetic field will drive motions, and these motions are almost incompressible, and they're like alpha and wave modes. And so these will induce, for example, if you have velocity perturbation, that will induce a Doppler shift. And you can look for that Doppler shift. You can also look for the energy density perturbation that will induce scalar metric perturbations. That will induce temperature anisotropy. Gravitational waves will induce something. So this whole thing is the recent Planck constraint on the magnetic signal. I mean, for many years, the CMB community was completely independent of any turbulence or magnetic field, because cosmologists find it too hard to do either turbulence or MHD, mostly. They love that smooth cosmology, dark energy, dark matter, nothing matters, all those things. So, okay. But very interestingly, I think some of the CMB people have also, I mean, we were calculating this from 98 with John Barrow and Seshadri and all, but they all kind of suddenly woke up to the fact that they can constrain one more thing. And so these are the latest constraint. This is the strength of the field at the scale of megaparsec, and there's a spectral index. -3 means a scale invariant spectrum in this language of the structure formation guys. K cubed P of K is the energy per unit logarithmic interval. So if P of K is K to the -3, then there is democratic power on all scales. Okay? So basically you can rule out everything which has got large scales. But if you produce blue spectra, it's very difficult because the CMB is sensitive only up to L of maybe 5,000–6,000 right now, except for ground-based experiment. they correspond to very large scale larger than about megaparsec or so. So very small scale power in magnetic field is not easy to rule out by this kind of thing, but it could lead to dissipation, ionization, heating, which changes the last scattering surface, and so that can also be constrained. Okay, so I will just leave you with some final thoughts. I'm maybe a bit hurried. That I think, it's very interesting that the universe is turbulent and magnetized, and dynamos are needed to maintain the fields in collapsed objects, but how to get fields in the voids? The first fields could be generated from early universe phase transition. Helical fields are particularly interesting. You need compelling generation mechanism, and primordial fields can leave signatures in CMB and structure formation. And there are sub-nanogauss limits right now, and there are future probes which are coming online. Very simple radio astronomy probes for the rotation measure, high energy cosmic rays, gamma rays, which I already told you about. I'm sure that I kind of talked about many things which are completely new to many people. So it has just been a rapid overview, and it's just to give you a flavor where the subject is. I'm sorry if I've confused some of you, but thank you very much for your attention.
Questions?
With sub-nano Gauss now.
Yeah, for example, the sub-nanogauss limits are coming from something which I didn't talk about, which is the non-Gaussianity because the magnetic field, suppose, is Gaussian, the Lorentz force is intrinsically non-Gaussian. So any signature of magnetic fields in the CMB will have non-Gaussianity features. So we have, with Pranjal Trivedi, we calculated many of these. And so from the fact that you don't see this non-Gaussianity in the standard way in which people analyze things, you can put limits, and that's where sub-nanogauss comes. Sub-nanogauss can still be interesting because suppose you take a field of 10 to the minus 10 Gauss, and you flux freeze it when you form a galaxy. This would be a million times overdense. So 10 to the 4 you gain, so you'll get a microgauss. So simply it will do various things. It may not be interesting for the nuclear synthesis because the energy density is 3 microgauss as redshifted to today. So sub-nanogauss is 10 to the minus 8 times the energy density at that time. It doesn't do anything there. But if you, sorry, we can continue.
Hello? Yeah, so, yeah.
You could give me some intuition. So when the universe expands, I understand that it frees the magnetic field from the flux freezing constraint and things of that sort. The classical...
the inflationary stage, not in the later when you have charge.
Yeah, no, I was talking about the inflationary state itself. Yes. So the general intuition I have is that if you expand something, any structure you may have just might wither away and vanish rather than building something. Isn't that what is supposed to happen in this case?
Thanks for that question, because I didn't have time to say all this. That basic electrodynamics is conformally invariant, and many of the theories of the particle physics are invariant under the scale transformation. So exactly what you say will happen, that the magnetic field will redshift away as 1 over expansion squared, and because of which it will go to very small levels. So what people do when they try to generate fields is to break this invariance by coupling it to something else. So here, for example, many popular theories couple it to the inflaton itself, and in this very simple way where you have electromagnetic action. So the wave equation, instead of becoming just a double prime plus k squared a equal to 0, gets an extra boost term. And then depending upon how you boost it, you can make this 1 over a squared become 1 over a to some epsilon. And that's what is required. And it's very exponentially sensitive. So it's not this would be a better theory because it's all natural, everything will happen. Inflation is not yet a very natural theory, but it's something which allows you to get big scales. But it has a problem of small amplitude, unless you fine tune everything. if you don't do anything to any conformal breaking, conformal breaking can occur in different ways. For example, if you have a higher dimensional universe, then the extra dimensional evolution can couple back to the normal things. But the most natural thing to expect is very small levels of in inflation. But phase transitions, we don't know how. So my approach until now has been to try to use observations to limit what is the possible amount of strengths and scales of the fields that we can infer from observation. So they are all upper limits. The first time gamma ray astronomy has tried to give you a lower limit, and now you have to try to see how to explain that.
Hello, hi. So my question is about the effect of self-gravity on the turbulence, especially I'm asking in the context of in the time scale, which is very small compared to the evolution expansion time scale. In that context, when you have baryons falling in the dark matter potentials, so the flow is very turbulent, and then they give rise to also these smaller scales collapse objects like galaxy clusters, then galaxies, and then stars. So these are very interesting implications on the initial mass functions. So how does this self-gravity changes the standard turbulence spectra? Because it's not a standard stirring in the box thing.
Yes, absolutely. For example, Sharanya's simulation, which was this one, is a simulation of a formation of the first star due to self-gravity. So in this particular case, the clumpiness which you're talking about doesn't occur because there's heating and cooling going on. It's not possible for smaller clumps to become genes unstable. And so here it is okay, you just get vorticity, this thing and all. But you're right, whenever, for example, in the interstellar medium, it's highly inhomogeneous. And the way the whole thing works, the way the turbulence works, supernova driving, clouds being there, it's not at all exactly like this box with uniform thing and all that. People have tried to simulate that, but the more processes that you put in, the more cost that you have to pay in terms of either resolution or what you. For example, there are direct simulations of the galactic dynamo. Have shown the field increases, and there you get a large-scale field, but don't show these fluctuation dynamos. So it's an evolving thing, I should say.
So has there been a study that the fluctuations there are not the standard fluctuations that we see like in Kolmogorov?
Well, for example, in this, in those simulations, you mean? Yeah, there is not enough scale to say all those kind of things. There's, of course, observation. There's supposed to be this great power law in the sky, starting from scintillations to rotation measured fluctuations, which is all supposed to be Kolmogorov in the interstellar medium. But numerically, you can't resolve those huge number of scales. But here, for example, in this box, of course, you see something minus 5/3 if you want.
Thank you.
Any more questions? Okay, if there are no more questions, let's thank the speaker for the very interesting talk.